So guys, last time we started off on registers, and we started off with the foundations on how registers operate, how registers are made from the flip-flop circuits, and I demonstrated a D flip-flop on my breadboard just to remind you on how the flip-flop really operated and how it could store a single bit data like 1 or a 0. So that's the basic foundation of how registers are made. And if you can remember, we said that registers are made from a combination of this small memory cell. So this is a single memory cell able to store a 1 or a 0. And we said if we can make a circuit able to store a 1 or a 0, then it means we are able to store a data like 1 1 0 1, or any other combination that you want, or any other bits. This is a 4-bit data, meaning that since a single flip-flop can store a single bit, so we can combine like 4 other circuits like this one in order to store a 4-bit data able to store information like 1101 or 1011 or any other combination that you have. So and I showed you how they are connected. So this connection that you're seeing on the bottom here is just a connection of a parallel input, parallel output. So today I'm going to explain to you the different registers that we have there, and mostly what we are going to deal with are the shift registers. The shift register, what I mean by a shift register is just a register that is able to store data or to shift data from one bit, from one memory cell to the other, then to the other, then to the other, and so on and so forth, for the purpose of memory, for the purpose of storing the information. So when I feed data in this point, it's going to be shifted from one memory cell to the other one, to the other one, to the other one, being controlled by a single clock input, which is connected to each one of those memory cells together. So every memory cell has its own clock, but the clock is just the same as the other one. The clock is just a single signal which is fed into each clock input of those cells, those memory cells. So having said that, today as we've said, we want to start on a shift registers, and I've just explained what a shift register is. So we have different types of shift registers out there. We have let's start with, we have a parallel input, parallel output. Let's just call it that. This is number 1. Parallel input, parallel output, shift register. This is an example of a parallel input, parallel output shift registers. You can see it has input which you feed data into each memory cell at a single at the same time. Then when the clock pulse is high, then they are going to be shifted to the output, meaning that we are storing the data at the same time. So at the same time you put the input, when the clock is high, it's going to be shifted to the output. So this is the output, this is the data output section. So this is a parallel input. You are inputting your data into parallel manner, then you're getting it out into a parallel manner. So that's basically what parallel input, parallel output shift register looks like. Then we can have another configuration, parallel input, serial output. Parallel input, serial output. So parallel input, serial output basically is just the same as this one, parallel input. The only difference is now, rather than having a parallel output like we have here, these outputs are connected to each other to get one single output. So that's a serial output. So you enter your data in parallel manner, then you get it out into a single wire serial output. That's why you call it a serial output. Okay, we have another one. Let's go with the serial input, serial output. serial input, serial output. So for a serial input, serial output, okay, let's go serial input, parallel output first, then we are going to go with the serial input, serial output as the last one. So serial input, parallel output, we have data being fed in a single line here. Rather than having four wires for feeding data, we have a single wire feeding data. Then the output is just the same like this one, you can see here. So we feed data in a specific point, then we get it out into different different memory cell. So that's a serial input, parallel output. Okay, hope you have understood that. Then the last one, we can have configuration looking like a serial input, serial output. So for a serial input, serial output, let me just demonstrate it. We can have maybe let me draw like this one, then the other point here, this, yes, like that. Then we have a single wire. So for a serial input, serial output, let's say we have a data here 1 0 1 1. So that 1 0 1 1 is being transported in a single wire. Then the receiver, let's say this is a transmitter, and this we can call it the receiver. So the receiver is going to get the data 1 0 1 1 like that, using just a single. So we have just a single input line, and we have a single output line. There is no parallel output, so meaning that these connections are not there. So it's a serial input, serial output, serial input, serial output. And this configuration is actually very helpful in modern day technology. You can say, let's take for example, we have a building, and we want to transform information from one point to another. So rather than having different wires to transform that data to the other part that we want, we can have a single wire which is just feeding the data directly. Let's say for maybe a remote control, and the receiver. Let's say this television set. This is a television set. So this is a wireless transmission. Actually, it uses a serial input, serial output. You can see this transmitter transmits information in a serial manner, so that the data can be fed into this receiver of this receiver. Then it can be manipulated into what you want it to do. So the serial input, serial output is very useful in modern day technology, and to do many or a couple of technology out there. So this is a circuit that I made. These are 2-bit. It's what I have in the breadboard. So these are 2-bit. You can see these are 2-bit memory cell. We have connected 2D flip-flop circuits together. Then the clock, we have inverted it to the other memory cell. Why? Because we want it to be a shift register. We don't want, when we feed data, the data is transformed into all flip-flops at the same time. We want it to move from this section, then it moves to the other section, then it moves from here to the other parts of the circuit. So in order to achieve that, we need to invert maybe the clock signal, so that the data can be transformed or can be processed in either the rising or falling edge of the clock. In either the rising or the falling edge of the clock, the data will be processed. Okay, if you connect, for example, for this, you can see the clock signal is just the same. For this one, the data can only be processed in the rising edge of the clock. When the clock is high is when the data can be processed. But for our circuit here, the configuration can process data in either the rising or falling edge of the clock signal. So that's what we wanted to achieve, and we have the data here as K0 and K1. If we feed data here, like let's say 1, we want to feed 1 0, then we put 1 in the first falling edge, put 1. So 1 is going to process here. It's going to give, or we put 0 first. Put 0 first. We always start for a bit like this, for an information like this, we start with this is the least significant LSB. Let me just write it well. We want 1 0. So this LSB, and this is MSB. So this means the least significant bit, and this is the most significant bit. So least significant bit first into the D flip-flop, then the next clock pulse we put 1 into a D flip-flop, then it stores that information. Yes, like that. So the circuit is right here. You can see we have connected two D flip-flop. For the first D flip-flop, it uses these two integrated circuits. It's an AND gate and a NOT gate. Then the other one is using these two integrated circuits. We have an AND gate and a NOT gate, just the same. Here we have the clock pulse we have the clock IC, which is NE555, connected in oscillator mode. Then we have our capacitor right here. I'm using a 470 microfarad capacitor, meaning that it's going to be a bit slow, because that's what I want to achieve in order to explain what the circuit is really doing. Yeah, but for a real-time circuit, remember, as I said, the time, the clock is measured in nanoseconds, because we want our devices to be fast. So when we type something, we want it to be on the screen almost immediately. So for that reason, the clock pulse is usually very fast compared to this one. I'm just using this just to explain to you and to show you what really happens inside of these processes. So I'm going to turn on my circuit, and we are going to start the demonstration. So remember, as we said, our circuit, we have just connected, we have just inverted the signal here, the clock signal, to the other D flip-flop, because we want to shift data from here. So for the first D flip-flop, it's going to process data when the clock is high. When the clock is high, in the rising edge of the clock. Then for the falling edge of the clock, the other flip-flop is going to process the data that it has from the output of the first data flip-flop, like that. So when I put 1 here, we expect the first LED to be on when the clock is high. Then when the clock is turned off, then the other LED is going to be turned on, because it's getting information from this part of the circuit. It's getting information from this part of that circuit. Okay, so that's what we want. So let me turn it on. So the first one is off. Then when it turns off, it transforms that information to the other flip-flop, and it remains on because the input is on. You can see the input on. If I turn the input off, then it's not going to turn all of the data flip-flop off. It's going to turn off the first one first. Then for the next edge of the clock, it's going to turn the other D flip-flop. So let's do that. Then it's off. Then this one is the one that turns off first, then it goes to the other one when the clock is low. Okay, so you can see that this one is only activated when the clock is high, and the other one is activated when the clock is low, for the purpose of shifting data. So we are going to do that again. So when I turn it on, this one is the one that's going to be turned on first. Then the information is going to be shifted to the other LED when the clock is low, because this other one conducts or processes the data when the clock is low, on the falling edge of the clock. So let's do that again. It's on, then on the falling edge the other one is on. So when I turn it off, we will start with the first flip-flop turns off, then on the falling edge the other one process the data and is turned off. So that's basically how the shift register operates. It shifts data from one flip-flop to the other one depending on the connection of the clock, whether it conducts in the falling edge or the rising edge of the clock signal is going to process that data. So I hope you've really understood on how the shift register operates. Next time I'm going to use an integrated circuit to demonstrate the parallel input and the parallel output of registers. Then we are going to move on from that point. So this for now, we call it the 2-bit register able to shift data. So we can call this a serial input, serial output, because we have only one input as the input and the other 8. So in this section right here, the output, I'm using the output from the first flip-flop, then from the other flip-flop, because I want to demonstrate, I want to show you how the information is shifted from one point to the other. For a serial input, serial output, it should have only a single output line and a single input line. Okay, I hope you've understood that. But because I want to demonstrate, I've used two output lines for you to see. So this for now we can call it a serial input, parallel output, because we have two output lines. But if we could have just a single one, it could be a serial input, serial output register. So I hope you've really understood. And yeah, next time we are going to check on how we are going to see on how a parallel input, parallel output shift register operates, and we are going to move on from that point. So thank you very much guys for watching. Please subscribe to Tronic Zenergy, where we do fun stuff all day, all time. So till we meet next time, goodbye.